In our last lesson, we introduced the conditional, so P implies Q, and the biconditional, P if and only if Q. And what we saw is that for the if-then, the truth table differs from what we expect it to be in the case when P, the premise, is false. And in fact, we have P implies Q. It's always true, with the exception of when the premise, P, is true, but the conclusion is false. Otherwise, we have that P implies Q is true. However, with P if and only if Q, what we have is that this is true whenever P and Q have the same truth value assignments. As we see in the first row, P and Q are both true, and in the last row, where P and Q are both false. But in the two middle rows here, we have that P if and only if Q, that it is false, since their truth value assignments differ. Now, a distinction that is to be made is in our use of if-then in everyday language, which at times can be taken to be a biconditional. But in mathematics, we need to be extremely careful, since if-then is not equivalent to if and only if. There is one distinction where in mathematics we don't write if and only if, and that is in definitions. So for example, let's go ahead and define what it means to be an even integer. So definition, we say that an integer x is even if there exists some integer k such that we can write x as equal to 2 times k. But now, in this definition, this if, as in every definition in mathematics, it really is an if and only if. We just go ahead and omit the if and only if and just write if. And so similarly, we can go ahead and define what it means to be an odd integer. So we say that an integer x is odd if there exists some integer k such that x is equal to 2k plus 1. And so we have our definition of what it means to be odd. And once again, we use if, but we really mean if and only if. And so that's the only exception in mathematics where we write if. It is taken to be an if and only if, and we drop that extra f. But now, if we had the following statement, which I'm going to go up here and write, to emphasize the distinction between if-then and if and only if, let us consider the following redundant example. If x is an even integer, then x is an integer. So again, this is redundant. We know by assumption that x is in fact an integer. So we have x is an integer, and we have x is an even integer, and we have x is an integer. And so this is a statement of the form P implies Q. But now, if we do Q implies P, this is telling us that if x is an integer, then x is an even integer. But now the premise is saying that every integer is even, which is false. 3 is not even. And so now here we have that this is a false statement. And so the if-then is different than the if and only if. And so the if and only if is now when two propositions are equivalent to each other. And so in other words, we have necessary and sufficient conditions for P and Q. And so this is the phrasing that we introduce in our last lesson. So before we move on, I'm going to go ahead and introduce some terminology. So we were looking at P implies Q, and we were looking at the reverse implication, that is Q implies P. We're going to call that the converse. This is the converse of P implies Q. And so definition, we say that the converse of P implies Q is Q implies P. And so in order to have a biconditional, an if and only if, we require the converse of P and Q to also be true. Okay, so with that, let us now talk about one of the conditional laws, which allows us to write implication in terms of or and not. So namely, we have that P implies Q is equivalent to not P or Q. And we can verify this directly with a truth table. So if we look at not P, so in this case we have not P will be false for both of these. And so we end up getting that this here would be true since Q is true. But then not P in the second row, that's false and Q is false. So we will have false in that entry. But then for the third row, we have Q is true, so this is true. And in the last row, we have P is false. And so not P is true, and so this is true. And now the truth tables are equal, and so we can deduce that in fact P implies Q is equivalent to not P or Q. We also have by De Morgan's laws that the statement P implies Q is equivalent to not parentheses P and not Q. And the way we do that is from the first statement, we can apply De Morgan's laws. And what we are going to do is do it in reverse. So we want to extract a not. And so we're going to extract a not. And that will give us a P and not Q. Since we know by applying De Morgan's laws, this will become not P or Q. And so we got the statement that is down here. And so that's what we get, the statement right below. So next we are going to be looking at exercise 3G from 1.5. But before doing so, let us discuss the only if phrasing. So in our last lesson, we had the table for the phrasing. We had in terms of sufficient and necessary conditions, if then, and so here we had the same exact two entries. So if P then Q, and if Q then P. But now I'm going to go ahead and erase this and write this differently. So P implies Q, we can also write as P only if Q. And so whenever we have the only if, that is referring that the antecedent is P and the consequent is Q. Whereas if we write P if Q, now Q becomes the antecedent, and so that's our hypothesis, and P becomes the consequent. And so now we have Q implies P. And together we have that P, if and only if Q, is now P implies Q and Q implies P, which by definition is P if and only if Q. So we have this here. So now let's analyze the logical form of the statement either it is windy if it is raining, or it is not sunny only if it is raining. And to do so, let's let W be it is windy, R it is raining, and S it is sunny. So here we have it. R is it is raining, S it is sunny, W it is windy. Now, a comment about our book, which I sent in an email. Whenever we have either or in Bellarmine, we mean inclusive or. In our text. And so with that, we have either it is windy only if it is raining, or it is not sunny only if it is raining. Now that statement is equivalent to the following. So the given statement reads as, so the only if, so that's referencing to windy. It is windy as the antecedent. And so here we have W implies R. And now the either or is referring now to this or inclusive or. And we have not sunny as appearing before the only if, so that's the antecedent there. So not sunny implies that it is raining. And so we have our logical statement. But let's now go through and reduce this further. And so what we are going to do is use the conditional laws. And so we have that P implies Q is the same as not P or Q. So let's go ahead and rewrite this. So I'm going to do a 2-column argument here. So we have W implies R, or not S implies R. This is logically equivalent by the conditional laws to not W or R or S or R. And so here we have used the conditional laws. But now the benefit here is that we have everything in terms of or, so we have nothing to worry about in terms of distribution. So we're going to reorganize this so that we can bring the R together. So we have R. And so if we use associative and commutative laws, we can conclude that this here is going to be logically equivalent to not W or S or R or R. And so here we use the associative and commutative laws together. So we have this here. But now R or R is just equivalent to R. So this is what we refer to as in the book as the idempotent law. And we have not W or S, which, if we apply De Morgan's law, we can go ahead and extract a not out. So I'm going to extract a not, and that will give us a W and not S. And then, oops, that was supposed to be an or R. And so here we are using De Morgan. And idempotent law. So the idempotent law is for the R or R being equivalent to R. And so we have this here. But now we have our statement as a conditional, because now we have not this here or R, which now by the conditional law is the same as W and not S implies R. And so here we use conditional law. And so we are done. And so we have that the given statement is equivalent to saying if it is windy and not sunny, then it is raining. And now we get to one of the most important laws for our course, the contrapositive law, which says that P implies Q is equivalent to not Q implies not P. So we can go ahead and do a truth table to verify this. And so we know that whenever not Q is false, then the statement for the implication will always be true. And so in this case, not Q, it is false whenever it is Q is true. So this here and this here we're going to have true. And if we have that this here is true, so not Q, then this is going to become true. And not P, this is false, this will correspond to this here being false, since now we have that not Q is true and not P is false. And lastly, in the very last one, we have that not Q is true and not P is true, and so this will give us back true. And so we see here that this is logic equivalent. But why did I say that this is one of the most important laws that we will use in this course? Is that when we get into proving, proofs by contrapositive sometimes allow us to do proofs that we otherwise could not. Let us illustrate this. So I'm going to go ahead and copy the definitions we had for even and odd, and we're going to use this to prove that if x squared is even, then x is even. And so here is our statement, so our lemma, that we're going to prove if x squared is an even integer, then x is an even integer. So now if we try to approach this directly, what would happen? So before we get into the proof, let's discuss what happens if we went about this just by the definition. So x squared is even, by the definition, that means that there is some x, there is an integer k, such that x squared is equal to 2 times k. But now, here we are in trouble going forward because, okay, we have that 2 times k, but we want to show that x is an even integer. So we want to show that x is equal to 2 times L for some integer L. But this is problematic because we need to be able to extract an x from here. But k, the way we use the definition, we just have that this is just some integer k, some integer. As it stands, we are incapable of proving this, because in order to do so, we would require to take a square root or have knowledge of unique prime factorization, which we will prove later in the course. And so at this moment, this lemma cannot be proven. But if we use the contrapositive law, then we can prove it. So we can't do this approach just yet. We can do it later in the course. But if we apply the contrapositive, we can see the following. So the lemma, so by the contrapositive law, the lemma is equivalent to so we have, this is our P and this is our Q. So we have that this will be equivalent to not Q implies not P. And so we have the lemma rewritten. And so now this is the contrapositive form. And so we will have here, if x is not an even integer, but if x is not even, we're going to take this now for granted, but an integer is either even or odd. It can be both. And so if it is not even, it must be odd. So we're going to take that assumption implicitly. And so if x is an odd integer, so this is our not q, then not p. And so p is x squared is an even integer, so not p becomes x squared is an odd integer. And now this statement here is equivalent by the contrapositive law to what we wanted to prove. And so that's what we are going to do. And so here is just a restatement, rephrasing. So we have by the contrapositive law, the lemma is equivalent to the statement x is an odd integer, then x squared is an odd integer. And so it suffices to prove this statement. So suppose x is an odd integer. by definition, there exists an integer k such that x is equal to 2k plus 1. But then, when we take x squared, that's the same as 2k plus 1 quantity squared, which becomes 4k squared plus 4k plus 1, which is the same as 2 times 2k squared plus 2k plus 1, which is the same as 2 times L plus 1, where L is equal to 2k squared plus 2k. So therefore, x squared is an odd integer by definition. We have exhibited the existence of an integer L such that x squared is equal to 2 times L plus 1. And so we have that x squared is an odd integer, and consequently, the lemma holds. Since we have proven it's contrapositive. And so that's one of the benefits of the contrapositive, is that it allows us to prove a statement that at this moment we are unable to. But by switching it to the contrapositive, we completely bypass the error that we were facing, namely the fact that we had no tools for understanding this x squared. Whereas going from x to x squared, that is fine, because if we take x as an odd integer, then we can go ahead and square it by definition. But reversing the process, since we haven't spoken about square roots or prime factorization, that is approaching it directly right now is beyond our means. But here we have it. We have proven this statement by going to its contrapositive. And so this is going to be one of the recurring laws that we will use throughout the course, whereas sometimes we just cannot do a proof directly. So we go to its contrapositive and hope that we can prove it in that setting. So next we are going to introduce the universal and existential quantifiers. So these are the following symbols. So universal quantifier is written as a backwards A, and the existential quantifier is written as a backwards E. And these stand for all and there exists. So I'm going to write this down. So it stands for and so here we have for all, but also for each, any. And so these are all perfectly valid, or also every. So for every. And then the backwards E stands for there exists. Or we could also take it to mean in the same way that for all, for each, for any, for every, we can have also here for some. So next, a quantifier always comes with a variable. And so we can have for all, for every x, or for all x, for any x. We can also have there exists a y, or there is some y. And of course here there is some universe of discourse that we are referring to where these variables are coming from. Now the first thing we want to analyze is that the order of these quantifiers does matter. So for example, what if we had our universe of discourse? So let's go ahead and say that the universe of discourse is R, the real numbers. So I guess to be R. And let's consider the following. So we're going to write for every x, there exists some y such that x is less than y. And now let's reverse the process and then write there exists some y such that for every x, x is less than y. And so here we have our statements. Are these the same? All we have done is just reverse the symbols for every x and there exists. But here, we are saying that for every real number x, we can find some y that is greater than x. That is a true statement. If we choose our real number to say be 5, then we can certainly choose our y to be 6 or 7. And so there is some y. But now, this statement is not true. So I'll just write this here. This is true. But here in this statement here, we are saying that there exists some y such that for every x, where now x is a reference, the for all x is a reference to our universal discourse, so for every real number x, we have that x is less than y. So what does this say? This is saying that there exists a greatest real number and this is false. And so we now see that these two statements are not the same thing. Because certainly there is no real number y such that that real number is greater than every single real number out there. And so this is a false statement. And so whenever we are dealing with quantifiers, it is crucial to know that the order is preserved. So we cannot interchange for all x and there exists. On a similar vein, let's go ahead and take the following statement. We're now f of x and y, and now we're changing our universe of discourse. And so now Hugh is the set of humans. And so let's go ahead and say that f of x comma y means x is a friend of y. So if we write for every x, and so for all human, there exists another human such that f of x comma y. Now, this is saying everyone is a friend of someone. So that's one way of interpreting this in English, that every person has a friend, and so everyone is a friend of someone. But if we reverse the quantifiers, we get something completely different. In the same way that reversing it for the inequality x less than y, we got that there is a greatest real number. Now we have that there will be someone that is a friend of everyone. And so namely, we have there exists a y such that for every human, f of x comma y. And so now this here would mean there is someone who is a friend of everyone. And so in the homework, you're going to be analyzing various situations like these, just to get familiar with the use of quantifiers. And in our next lesson, we will talk about negating quantifiers. If we take the negation of for all, or the negation of there exists, what are going to be the corresponding quantifiers that we get back, and how would that affect the statements that we are looking at? But to finish it off for today, let us return to some of the definitions we have talked about and rewrite those definitions in the language of quantifiers. So in our last lesson, we discussed sets, and so namely, if we have two sets A and B, we saw that A is a subset of B if every element, and so now we have our universal quantifier, every element of A, is also an element of B. So we can write this symbolically in the following way. So A is a subset of B, can be written symbolically as the following statement. For every x, x is in A implies that x is in B. And in a similar manner, when we talked about equality of sets, that just meant that A is a subset of B and B is a subset of A. And so we defined this last time as well, that two sets are equal if A is a subset of B and B is a subset of A. And notice how in language, since we're talking about a definition, I'm using the word if. But as I mentioned at the start of today's lesson, when we talk about definitions, the if really is an if and only if. And so when I say two sets are equal if A is a subset of B and B is a subset of A, that is the if and only if, or equivalent. And so now we can go ahead and write this symbolically, that the sets A is equal to B can be written symbolically as for every x, x is in A if and only if x is in B. And so we have our symbolic statement for equality of sets. So now, let us use a symbolic definition to prove the following lemma. So here we have three statements. For any set A, the empty set is a subset of A is a subset of itself, and if A, B, and C are sets, with A a subset of B, B a subset of C, then A is a subset of C. So let us look at the first one. So for the very first one, this may seem like an automatic thing, but let's actually prove it, because with the empty set, why is it that it's a subset of every set A? Well, let's look at the definition of being a subset symbolically. So we are saying for every x, x is in the empty set. But x in the empty set is a false statement since this empty set has no elements. So for one, let us make the following observation. So by definition, the empty set, and so this is the null set, and it has no elements. And so, x in the empty set is a false premise. Since we cannot choose some element x in the empty set. And so now we have a statement of the form, false implies x is in A. And so now since this is false in the case of the empty set, and we have that the conditional is always true if the premise is false, then we end up getting that the whole statement is true. So consequently, x in the empty set is false, and thus x in the empty set implies x is in A is true. Therefore, the empty set is a subset of A, since now we have this is always going to be a true statement for every x, and so we have that we do satisfy the definition. So let us prove the second statement. So for the second statement, we have A is a subset of A. So let's go ahead and take X is in A. Then of course X is in A, but now we are implicitly assuming something here foundationally. What if A is the empty set? If A is the empty set, we can't choose an element from the empty set. So whenever we are starting a proof like this, we are implicitly assuming that the set itself is not empty, but we have any set A. So we want to go back and rewrite this. So we're going to break this down into two cases. Case one is the case where A is empty, and the second case is the case when A is non-empty. So if A is equal to the empty set, part 1 shows that the empty set is a subset of the empty set, since we had that this held true for any set A. And so now we can just go ahead and replace A with the empty set here, and we have that the empty set is a subset of itself, and so we got this. And of course these two are equal, but we want to prove containment right now. And so we have this situation. So now suppose that A is non-empty. Then X in A implies that X is in A. And so here we're using the sort of redundant argument we did in our earlier example when we were looking at the difference between implication and converse. And so we're, again, X is in A, and we're just concluding X is in A. So we really have not done anything. But we are using the fact that A is non-empty so that we can choose that element X in A. But now, by definition, we have X is in A implies X is in A, and that will hold for every X, that X is such that X is in A, and so we do get, by definition, that A is a subset of A. And so by definition, A is a subset of itself. So lastly, let's look at 3. If A, B, and C are subsets, so if A is a subset of B, and B is a subset of C, then A is a subset of C. Once again, we want to eliminate the case when A is an empty set. So if A is equal to the empty set, then the empty set is a subset of C, and so we are done with this situation. So suppose that that A is not equal to the empty set. And now let's go ahead and choose an element in A. By assumption, X is in B since A is a subset of B. And that's what it means to be a subset of B, is that now that X is in B. And similarly, X is in C since B is a subset of C. And so now we have shown that if X is in A, then X is in C. But whenever we're doing these arguments in this manner, we're choosing an arbitrary X in A. And that's where that for all X is coming in, is that we're choosing an arbitrary element. And since for that arbitrary element we have that X is in C, we know that this holds for every X in A. And so thus, we can conclude that A is a subset of C, which finishes the proof of this lemma. So for our next lesson, we are going to go ahead, continue discussing quantifiers, but specifically how to negate the universal and existential quantifier, and then we are going to continue our discussion on sets by considering more operations on them.